All right, we've started section 3.5 twice. That's how much fun we've had with 3.5, and we're going to do it again a third time. All right, so today we're going to take a look at mental mathematics. I know I've mentioned this before when we did mental mathematics in 3.4, but the whole idea is that what you're writing down shows me what's going on in your head. Not for the purpose of it had to be written down for you to do it, but just for you to be able to show me what you're thinking. That's the idea, okay? Because I can't grade your brain. I would love to, but it doesn't work like that. So we're going to take a look at mental mathematics with multiplication and division. So the first one we're going to look at is called front-end multiplying. Okay, so the way that front-end multiplying works, again, there's two components of what we're going to do. First, we're going to do mental mathematics, and I think then we're doing some estimation. Yeah, that's right. So we're finding exact answers. We're just finding the answers in our head. Okay, that's what mental mathematics means, not approximations. It means really finding the solution. So when you're taking a look at something like this, front-end multiplying is the idea that, again, no matter how large the number were, you're going to actually multiply it component-wise. So you've got the number 46, so you're going to multiply 40 times 5, which would give you what? 200. And then you're going to multiply the 6 times 5, which would give you what? 30. And then you're adding the 200 and the 30 together to give you 230. Obviously, a two-digit number by a one-digit number is not so bad for this because you can continue to think of one number in your head while you're doing the other calculation to add to it. This becomes increasingly difficult and probably not so mental once you add just a third digit to the top or a second digit to the bottom, right? Because you have to keep track of so much more as you go. But for a two-digit times a one-digit number, front-end multiplying looks something like this. Now, we've seen one called compatible numbers before. Compatible numbers is the idea that some numbers are easier to multiply together than others because they are compatible. And in particular, we like numbers that result in giving us something with a 0 in them. Zeros are our friend, right? Because they're easy to multiply with once you get one in the problem. So we're looking for two numbers or whatever that we can multiply together and get something with a 0. Can you give me a pair here that will do that? 5 times 2. Okay, the very end. So this is 5 times 2, that's 10. Can you give me another pair that when you multiply them together, you get something with a 0? You can either do the 5 times 4, or you could do
any number times the 10.
8. Well, we'll get to the times the 10 in a minute. We're just going to put a pause on the 10 for a moment. So you could do the 5 times 4, or you could do the 8 times 5. Either of those pairs. So this one would have two options. This is the one you guys told me, so I'll go with this one next. That's 20. So we've got a 20, we've got an 8, and we've got a 10. Agreed? And I don't really know that there's a better or less better. That's not right, but you know what I mean. There's really not an easier or a more difficult way once you get to this step with these three particular numbers. Sometimes there might be, right? I mean, like that's possible. But on this one, it's not too bad. So if we did 20 times 8, we would get 160 times 10 would give me 1,600 or 1,600, right? Okay, lots of zeros. We like the zeros. If you wanted to multiply the 20 times the 10 first and get 200 and then multiply that times 8 because that looked easier, go with it that way. You're still going to get the 1,600. All right, the next two is ones that you may not have ever thought like this before, and hopefully when you look at that you're going to be like, oh wow, that was really cool. Didn't know I could do it like that, okay? You're going to do, these are called thinking money. The idea with thinking money is that there are coins that we have that are worth certain amounts. And if you see that amount inside of a problem, it's often easier to think of the coin that goes with this. So this may or may not be super duper helpful for the tiny little one who's never worked with coins. Agreed? But some of the kids in your classroom will have worked with coins a fair bit, and you'll teach them that too at some point in first or second grade, working with money as well. That's actually something that's in your curriculum. So we're going to think of the 5 like what coin? A nickel. So just in terms of what this is basically saying we have 46 nickels. That's the idea that we're thinking when we see 46 times 5, we think I have 46 nickels. Now, I don't know about you, but there's a coin that's easier to work with than a nickel. Okay, I think dime. Why would I like dimes better? Any idea? Because it has a 0. That's exactly right. Okay, so now think about it. If I have 46 nickels, how many dimes is that? 23 dimes. Okay, right? So half the number of dimes because the coins are worth twice as much. 23 dimes. But when 23 dimes is like saying 23 times 10, right? Which is what? 230. Now, what we did actually has a property. What we really did with these numbers is we took this number and we multiplied it by 2, and we took this number and we divided it by 2. And there's nothing special about 2. We could have multiplied one by 4 and the other one and divided it by 4. We could have multiplied one by 3, divided the other by 3. It's just that this works really nicely with this, going along with the thinking about money, because we have coins of these values. So this property of multiplying and dividing the two numbers, it's almost like when we were doing the trading off algorithm for addition and subtraction. I add 2 here and I subtract 2 there, right? Or with subtraction, I subtract 2 from both numbers or add 2 to both numbers. But multiply one by 2, I can divide the other one by 2, and then it will keep the value the same. How about this one? There's a 25 in this one. Looks an awful lot like a quarter, doesn't it? Sure does. So this is 44 quarters. What would be the same as 40? Okay, so what would be the same thing as 44 quarters? $11. And a dollar is the same thing as the number 100 in our argument of what we're doing in terms of pennies or cents, right? So this would be saying like 11 times 100, which would give me 1,100. Now going back to my 25, what I really did, I'm sorry, I did that wrong, is I multiplied this by 4 and I divided this by 4. Like mathematically, numerically, that's the equivalent of what I've done when I've thought about it in terms of money. Okay? So coins are really helpful when the certain values are present. If you didn't have a 5 or a 25 here, it wouldn't be helpful. Make sense? All right. Breaking up the dividend. This is another one. So this number says 6,318 divided by 9. So this one, the idea would be that we take the 6,300 and 6,319 and we divide it into 6,319. So 6,300 divides very nicely by 9 if you know your multiplication tables. So what is 63 divided by 9? 7. And so 6,300 divided by 9 would be 700. I wrote 19 and I meant to write 18. Thank you. Okay, so there's 700. And then the 18 divided by 9 would be 2. So my solution is 702. This is a very similar one. It actually doesn't have the right title on my screen. It should say using compatible numbers, although it goes along very well with the breaking up the dividend. On the last one, what we did is we took 6,318 and we divided it to 63 and the 18, basically. We wrote 63 with the hundreds on it and the 18 with the other. So this is the idea here as well. So we're going to take the 425 and we're going to write it as the 400 and we're going to write it as the 25. And the reason we did that is because those numbers are both very nicely, evenly, simply divided by 5. So what would 400, well let's just start with 40. What would the number 40 divided by 5 be? 8. So the 400 divided by 5 would be 80. And then 25 divided by 5 is 5 for a grand total of 85.
So how is that different?
It's different in the sense that we didn't have to divide it up necessarily with the numbers that, like on the one before, I took the 63 because it was evenly divisible, but like the number 4 is not evenly divisible. Do you see what I'm saying? It's almost like I separated it to give me the 400 because 40 worked, whereas before the individual numbers you were seeing worked. The 63 worked, oops, that's not what I meant to circle. The 63 worked and the 18 worked all by their own. And this one you can't see that, like 4 doesn't work, but 40 does. Do you see what I'm saying? So it is very much the same once you get it broken apart. It works identically, but you don't see it very obviously, at least not as obviously as the one before, because the number itself, 4, is not divisible by 5, but 400 is. Yeah. All right. Last two examples are estimation. Circle, box, bold, highlight. This is estimation. Every time I do questions on tests about mental math and estimation, somebody, and it's usually more than one somebody, does one of the other that they weren't asked to do. They're told to use mental math and they estimate. They're told to estimate and they use mental math. Okay, so please, I don't know what you need to do on your note card to remind yourself, but do it. Okay, so that you don't get tripped up between those two. This is estimation. So, I mentioned before front-end multiplying. It was right here. This was front-end multiplying with mental math. You can do it in your head. And I mentioned it was because it was a 2-digit number times a 1-digit number. And that's really the bulk of why we can say it's doable in our head. Once you get over here to the 3-digit number times the 1-digit number, that becomes more challenging because there's more to keep track of in your head. Okay, so that's the first issue. Second issue is that this one's asking you to estimate. So it's not asking you to find the exact answer, right? It's asking you to estimate. However, it does still say front end. So what does that mean? Well, it means we're going to use the first 2 digits, and we're going to do the same thing that we did with the numbers before. We're just going to, if you will, ignore the 6. So we're going to do the 300 times 4, and we're going to do the 80 times 4, and we're going to get that answer, and we're going to add them together, recognizing that this answer is not right. It's an estimate. So what is 300 times 4? 1200. And what is 80 times 4? 320. And what is 1200 plus 320? 1520. And already, even with those numbers the way they are, I'm not saying you can't do it in your head, but it's more challenging than the numbers we were working with on the other problem, aren't they? Just by the very nature of these particular numbers. So, we're not asked to find this answer, we're asked to estimate, and the estimate here is 1520. This is a front-end multiplying estimate. This one's compatible numbers. Again, this one's going to feel like that breaking up one over here that we were looking at, right here. 6318. If we were finding it exactly, it was really nice to see the 63 because it's a multiple of 9. Really nice to see the 18 because it's multiple of 9. When we did the 425, it was really nice because once we recognized that 4 meant 400 and it worked, and the 25 was nice and even, it was great. We're doing estimation on this one, and for estimation, this one says 4132 divided by 4. Our goal is to choose a number that's close to the 4132 that divides quickly and easily by 4. What's the best option? Easier than that. 4,000. Yeah. So 4,000, and Rebecca, that number would be fine. There's nothing wrong with it. It's just that you're going to take a little bit more work to get to that one. 4,000 would work. What is 4,000 divided by 4? 1,000. So the solution here, again, in estimation, that's not what I meant to do, is that this is about 1,000. Whereas this one over here is that it is about 1520. So on this one, let's say you saw that and you did not think 4,000, you thought something else. You didn't think of 4,000. You said, oh, I think it would be 40, we're just going to pretend, 4,400. Could you say 4,400 here? It wouldn't hurt anything. You'd be a high estimate, right? Whereas this one right here is a low estimate. But it'd still be pretty close. And the goal is to get pretty close, so it'd be okay. Sometimes a high estimate is actually desirable as compared to a low estimate, if you're depending on what you're estimating. So, all right, any questions about these two computational estimation examples or the mental math ones? All right.